Okay, Bismillah Rahman Rahim. Now, today is lecture number 6 and 7 of the course Irrigation Engineering. In today's lecture, we will study about design of irrigation canals. So, we already studied about Kennedy's cell theory in the previous lecture. We will continue with this theory again in today's lecture. Also, we will study about the Lacy's regime theory. After this, we will study about the canal lining, and we will also study about maintenance of irrigation canals. Now, the Kennedy's cell theory we discussed in detail in the previous lecture, and we discuss the first case. So, if you remember, this theory is a trial and error procedure. Now, in this theory, the first case that we discuss, the longitudinal slope must be given. So for that slope, we design the channel and come up with the dimensions of the channel cross section. So Kennedy did not give any equation for slope of the canal. This means the longitudinal slope. The slope is decided according to the ground available. From the plotted longitudinal slope of the alignment of the canal, there is always a certain range of slope that can be given to a channel at a site. If you remember, in survey chem, you plotted the profile level of the road. So if you remember, there were a certain range of slopes. So exactly in a similar manner, from the plotted longitudinal slope of the canal alignment, there is always a certain range of slope that can be given to a channel at a site. For every such slope, a separate channel can be designed to suit a given discharge. So this is what happened in the previous lecture. We solved a problem. For any given longitudinal slope of the channel, a separate channel. This means the dimensions of the channel, the bottom width and the depth of flow. In case of trapezoidal channel, can be designed to suit that discharge. For example, if we consider a discharge of 2 cubic meter per second, this is the rugosity coefficient and this is the critical velocity ratio. Now we get different dimensions for various slopes. You can see that in this table, if we design the channel according to the Kennedy's theory, now if you assume the slope is 1 in 5,000, we will get these values for the bottom width of the channel, and this is the depth of flow. We have this as the trapezoidal channel. So this is the bottom width, this is B. And this is the depth of flow, full supply depth. So the B by D ratio, that is 10.3. If we consider the slope as 1 in 4,000, then these are the values. You can see here that for every such a slope, a separate channel can be designed for a given discharge. Discharge is the same. For this 2 cubic meter per second, you can see that we will get these dimensions. So the B by D ratio is then 3 by 3.8. And if we consider the longitudinal slope as 1 in 2000, then the bottom width is 1.5 and the depth of flow that is 1.4, giving B by D ratio is 1.07. So it means that when we consider a different longitudinal slope, we will get the different dimensions for the channel cross section for that given discharge. Now the question is that which channel section that will best suit for the given situation. So you can see that this is one of the drawbacks in the Kennedy's silt theory, because Kennedy did not give any clue that which one would be the best. Unfortunately, Kennedy's theory provides no clue to which of channels will be best suited for a particular discharge and type of soil. Hence, some guidance is necessary to find out which channel would suit the need best. To provide this guidance, suitable B by D ratios were fixed in various departments, irrigation departments, on the basis of experience. So what happened? To provide a guidance that which channel section would be best for the given situation, for the given discharge and type of soil, suitable B by D ratios were fixed from experience. Clear? Wood's normal design table, which is available in the book Irrigation and Water Power Engineering by Pumia, is one such criteria which was prepared in Punjab and is very much in use. Thus, if B by D ratio is selected from the recommended values, one more equation is available and unique design of a channel can be done, including bed slope, using the Kennedy's theory. So what happened is that, if you remember in the previous lecture, we solved a problem. So if you change the slope, we get the different dimensions of the channel section. So the solution is not unique. If we fix this B by D ratio, so we can have unique design, means there will be one design of the channel. We will come up with the depth and the bottom width of the trapezoidal channel, including the slope, the bed slope, the longitudinal slope of the channel using Kennedy's theory. So you can say that this was an improvement on the Kennedy's silt theory. So that's why we discuss case 2. Now for case 2, the discharge, rugosity coefficient, the critical velocity ratio, and B by D ratio, these are now given. So how we proceed, and then we design the channel. So again, we have a step-by-step procedure. Now step number 1 is that calculate A in terms of D. Since this B by D ratio, it is given, so let B by D is equal to X, where X is some given value. So B will be equal to D times X. Now this is the area for trapezoidal channel section. A is equal to B times D plus Z. Z is the slope into D square. Now if we consider the side slope is half to 1, so this is Z here, as we already discussed. So this is the depth, full supply depth for the design discharge, and this is the bottom width of the channel section. and we have the side slope. So this is Z2 1. So let the side slope is equal to half ratio 1. Then this equation can be written as for area. Now this B we replace in this equation for area. We can replace this B. So this will be then equal to D square into X plus 0.5. Step number 2 is the value of V is known in terms of D by the Kennedy's equation. So this is the equation, this is the critical velocity that we calculate from the Kennedy's equation. So you can see here that in this equation, the values of V and A should be substituted in the continuity equation. We have this as the area, and we have this as the velocity for the equation that we can put in the continuity equation. Q is equal to A into V. So A is coming from here and V is coming from here. So in this equation, when you simplify, you can see here that in this equation, the only unknown is D. Because discharge is given, the critical velocity ratio that is given, X is given, this is B by D ratio. So the only unknown is the depth of the flow section, so that can be determined. Now, when depth can be determined, so step number 3 is we can calculate B, because B by D ratio is given. Now depth is known, we can calculate the bottom width, and once B and D are known, so then we can calculate the hydraulic radius or hydraulic mean depth. Step number 4 is that in this equation here, Kennedy's equation, the critical velocity that we can calculate, now that depth is known, so we can calculate the velocity from the Kennedy's equation. The critical velocity ratio M that is given. Clear? Now step number 5 is that knowing velocity and the hydraulic radius, we can determine the slope, longitudinal slope of the channel using the Chazy and Cutter equations. So this is the Chazy and Cutter equation. You can see here that we have the Chazy equation as V is equal to C into square root of hydraulic radius and longitudinal slope. So this is the Cutter equation. This value of C, this is coming from the Cutter equation. And we have square root of RS in the MKS system. In the FPS system, the equation we already discussed in the previous lecture. So in this equation, you can see that everything is known. This velocity is known. Rugosity coefficient is given. Hydraulic radius we have calculated. So the only unknown is the longitudinal slope, this S. Now this S, it is present in the numerator and in the denominator. So this equation can be solved by trial and error. So these are the design steps that we have to follow in case 2. Now let us try to solve an example. Design an irrigation canal with the following data by Kennedy's theory. The discharge is 14 cubic meter per second. Rugosity coefficient is 0.0225. The critical velocity ratio, that is 1, and the B by D ratio given is 5.7. So let us try to follow these steps and we solve this problem. So step number 1, we have the step-by-step procedure. So step number 1 is we have to write down the equation for the area. The channel that we consider is the trapezoidal channel section. So as B by D ratio is given, so this B by D ratio, that is 5.7. Now this can be written as B equal 5.7 times D. Now we have the equation for the area A. So this is the general formula for a trapezoidal channel section. B times D plus we have Z, which is the side slope, into D square. Now for side slope, Z ratio 1, we consider half to 1. Then this equation for area A, it becomes B into D plus D square by 2. Now B is equal to 5.7 times D. So you can see here, if we take out this D square common, so this will be equal to B by D plus 0.5. Now B by D, that is given 5.7. So this is equal to D square 5.7 plus 0.5. So this area A, this is now equal to 6.2 into D square. Next we have step number 2. So step number 2 is that we calculate velocity V, that is from the Kennedy's equation. So we have V is equal to 0.55 for this system of units into m, the critical velocity ratio, into D 0.64. Now the critical velocity ratio, it is given as 1. So this will be equal to 0.55 into 1 into D power 0.64. So this equation for V becomes a 0.55 into d power 0.64. Now we have the area equation, we have the velocity equation. So Q is equal to AV. So this will be equal to 6.2 into d square into velocity, that is 0.55 into d power 0.64. Now in this equation you see discharge is given 14 cubics. So the only unknown is d. So d we can calculate from here. D, this will be equal to the discharge divided by 6.2 into 0.55 and power here we have 2 and 0.64. So 2.64 comes on the other side. So this will be 1 divided by 2.64. So now just plug in the values. So we will get a d that is equal to 1.71 meter. 1.71 meter. Once a d is known, then we can go to step number 3. And now b by d ratio is given, we can calculate b. So this is 5.7. So this will be equal to 5.7 into a d. Now just put the values of d as 1.71. So this comes out to be 9.75 meter. Similarly, we can calculate the hydraulic radius. So the hydraulic radius, that is equal to flow area divided by the wetted perimeter. So this will be equal to b times d plus d square by 2 for the given side slopes, and the wetted perimeter, that will be equal to the bottom width plus d into square root of 5. So if you plug in the values for the b and d, so we will get this is 1.34 meter. Now step number 4 is that we have calculated the depth. We can calculate the critical velocity from the Kennedy's equation. We have 0.55 into m into d power 0.64. So just put the values, everything is known. So the velocity comes out to be 0.775 meter per second. Now the area is calculated already. The velocity is 0.775. Now step number 5 is we use the Chezy-Cutter equation. Chezy and Cutter equations. So that equation is that V is equal to, take care of the system of units, 23 plus 1 divided by n, rugosity coefficient, plus we have 0.00155 divided by 1 plus 23 plus 0.00155 divided, we have n rugosity coefficient here, into square root of r, and this whole multiplied by r. Now in this equation you can see that we have s here, we have s here, the longitudinal slope, and we have s here. So V is known, everything is known, hydraulic radius is calculated, rugosity coefficient is given here, you can see. So the only unknown is S. Now S is present in the numerator and in the denominator. So solving by trial and error. Solving by trial and error. So we will get the value for this slope of the channel is equal to 1 in 4940. So this is how we proceed to design the channel irrigation canal using the Kennedy's theory when B by D ratio that is given. So you can see here the advantage of this B by D ratio, that we have unique design, and also you see that we get the value for the longitudinal slope of the channel. Clear? Next we discuss drawbacks in Kennedy's theory. So Kennedy did not realize the importance of B by D ratio, as we already discussed in detail. So he did not realize the importance of this B by D ratio. Similarly, he did not define the silt grade, the size, and the silt charge, the quantity of silt load. He did not give any relation between velocity of flow and water surface slope. Empirical relations between velocity, depth, hydraulic radius, and slopes were found to determine a stable cross section. So empirical relations, what is the drawback in this point? That you develop the empirical equations from a set of data. Now the empirical equations fit only that data. So it means that if we have other conditions, then these equations may not be applicable or may not give satisfactory results. So this is normally the problem with the empirical equations, that their application is limited. To similar cases you can apply, but not all the cases. He did not give any relation for the calculation of bed slope of the canal. The bed slope could be adopted as per the ground conditions. Similarly, he did not account for silt concentration and bed load separately. He accounted all factors in one single factor, that is the M, critical velocity ratio. For the design of a canal, he aimed to achieve the average regime conditions. And for the determination of mean velocity of flow, he used the Cutter's equation. Thus, the limitations of the Cutter equation were incorporated in his theory also. So these are the drawbacks in the Kennedy's theory. So next we discuss the Lacey's regime theory. Lacey, an eminent civil engineer of UP, United Provinces Irrigation Department, published his first paper through the Institution of Civil Engineers, London in 1929. He carried out extensive investigations on the design of stable channels in alluvium. On the basis of his research work, he found many drawbacks in Kennedy's theory. It was stated by Kennedy that a channel is said to be in the state of regime, that is a stable channel, if there is neither silting nor covering in the channel. If there is no silting and no covering, the channel is stable, and that is the state of regime. A channel is said to be in regime. But according to Lacey, even though a channel with no silting and no covering may actually not be in regime. So Lacey therefore differentiated between three regime conditions, that is true regime, initial regime, and final regime. So what are regime conditions? A channel is said to be in a regime when the following conditions are satisfied. Number one is the channel is flowing in an unlimited incoherent alluvium. So what is meant by incoherent alluvium? It is a loose granular material which can be scoured out as easily as it is deposited. Loose granular material which can be scoured, removed as easily as deposited. That is known as incoherent alluvium. So the channel is flowing. This is requirement for the regime condition, that the channel is flowing in unlimited incoherent alluvium of the same character as that transported. Discharge is constant. Silt charge is constant, that is the amount of silt is constant. Silt grade is constant, the size, and the flow is uniform flow. Hence, a designed channel is said to be in true regime if the above conditions are satisfied. So if these conditions are satisfied, then we will say that the design channel is in true regime. But in practice, all these conditions can never be satisfied, and therefore artificial channels that we design can never be in true regime. Hence, Lacy gave the idea of initial and final regime for actual channel. So what is initial regime? One of the conditions of attaining a regime of a channel is that there should be freedom for the channel to form its own section. Initial regime is the state of channel that has formed its section. Section means the cross section. Clear? Cross section of the channel. This is what we mean. So initial regime is the state of the channel that has formed its cross section only and yet not secured the longitudinal slope. This is initial regime. So what we mean by initial regime? Bed slope of the channel varies. See, yet not secured the longitudinal slope. If a channel is constructed in defective slope, what will happen? Naturally, the channel and the flow conditions, it will try to establish a longitudinal slope that is appropriate. Clear? Naturally, because this is unlined channel. So that's why in the initial regime, the channel will be such that yet not secured the longitudinal slope. The cross section or wetted perimeter remains unaffected. So initial regime is the state of channel that has formed its section, means the cross section only, and yet not secured the longitudinal slope. The final regime, if all the variables such as perimeter, depth, slope, etc. are equally free to vary and finally get adjusted according to discharge and silt grade, then the channel is said to have achieved permanent stability, called final regime. This is the final regime. If all the variables such as perimeter, depth, slope, etc. are equally free to vary and achieve permanent stability, this is known as final regime. Regime theory is applicable to such channels only. We continue with this discussion. Such a channel in which all variables are equally free to vary has a tendency to assume a semi-elliptical section. This is according to this theory. This is what this theory says. Such a channel in which all variables are equally free to vary has a tendency to assume a semi-elliptical section. This is what this theory says. So you can see here channel shape carrying coarse silt. So this will be the shape. It will have shallow depth and wide section. You can see here the section is wide and the depth is shallow. This is the channel shape carrying coarse silt. If the channel carries fine silt, this will be the channel shape. It will be narrower in width and it will be deeper. It will be narrower, the width will be narrow and the depth will be more. This is how the channel will assume these shapes. This is according to this theory. So the coarser the silt, the flatter is the semi-ellipse, that is greater is the width of the water surface. As I already explained here, the finer the silt, the more nearly the section attains a semicircle. The second point which Lacey argued was that the sediment is kept in suspension not only by the vertical component of the eddies which are generated on the channel bed, but also by the eddies generated on the sides of the channel. If you remember, we discussed in the Kennedy's theory. So Kennedy argued that the water is flowing in a channel. This is unlined channel. So because the water is flowing, there will be friction. So because of the friction, these eddies are generated. And Kennedy argued that the eddies which are generated from the bed of the channel, they are for most of part keep the sediments, the silt in suspension, does not allow the silting to happen in the channel. He stated that we can have the eddies from the sides of the channel, but for most part they are horizontal and have very little effect on the silt in suspension. But Lacey said that the eddies generated from the sides of the channel, not only the bed, but the eddies which are generated from the sides of the channel, also keep the silt or sediments in suspension. So Lacey argued that the silt supporting power of the channel is proportional to the wetted perimeter and not to its width as presumed by Kennedy. So Kennedy said only the bottom width of the channel, the eddies generated, keep the silt in suspension. So the silt supporting power, that was proportional to the width. However, Lacey argued that the silt supporting power of the channel is proportional to the wetted perimeter and not to its width as presumed by Kennedy. And as per the Lacey regime theory, this makes sense. You see here that this is the shape of the channel for coarse silt, and this is the shape of the channel for the fine silt. So you can see here that the wetted perimeter, it varies. So this makes sense what he said. Clear? Thirdly, Lacey argued that the grain size of the material forming the channel is an important factor and needs more attention than was given by Kennedy, because he bring everything in critical velocity ratio. Different values of critical velocity ratio for different types of soils. So Lacy therefore introduced a term known as silt factor in his equation and connected it to the average particle. So he defined this silt factor. Now, permanent regime, a channel is in permanent regime when its section is provided with a lining to protect against covering action, thereby imparting permanency to the channel section and longitudinal slope. A channel is provided with a lining to protect against this covering action, so thereby imparting permanency to the channel section and longitudinal slope. So regime theory is not applicable to such channels. That's why you see the Kennedy and the Lacy theory, we do not apply to the design of lined canals. These are for the design of unlined canals. Clear? So the design procedure for Lacy's regime theory, the design procedure involves no trial and error. For the channel design, the discharge and the mean diameter of the silt particles d sub mm, this is the mean diameter of the silt particle in millimeter, or silt factor should be known. So step number 1 is calculate the silt factor. Kennedy defined the critical velocity ratio, but in case of Lacy theory, he gave the silt factor, this equation here. So either the silt factor is directly given or it can be calculated using this equation where dm is the mean particle size in millimeter. Step number 2 is calculate the velocity. So Lacy give these equations for calculation of the velocity in MKS system and in the FPS system. You can see now the silt factor, it appears in these equations. So if silt factor is not constant, then you see here that this will become a drawback in the Lacy's theory. But now at the moment we discuss the design procedure. So the velocity can be calculated from these equations. Discharge is given and velocity is calculated from this equation. Area can be calculated from this equation, discharge divided by the velocity v. Step number 4 is to calculate the wetted perimeter P. So Lacy give these equations to calculate the wetted perimeter in MKS system and in FPS system. Step number 5 is find out the bed width and the depth d of the channel section. Since area and P are known, area and the wetted perimeter are known, so the side slope of the canal can be considered as usually half to 1. So we have these equations for trapezoidal channel. If the side slopes are half to 1, these are now the equations. Now in this equation you can see wetted perimeter is known and area is known. So we have unknown as B, the bottom width, and the depth. We have two equations. Clear? So these two equations can be solved in terms of two unknowns. to calculate the values. Or we can use these equations. D will be equal to, this is the area A, and for B, when D is known, it can be calculated using this equation. This is actually this equation simplification here. Square root of 5, that is 2.236. Step number 6 is to calculate the hydraulic radius. Again, Lacey give the equation. For the hydraulic radius, this equation and this equation in both the system of units, this is in MKS system and this is in the FPS system. We calculate hydraulic radius from here. Now, hydraulic radius can also be calculated area divided by the wetted perimeter. So the area and the wetted perimeter are also calculated. So you can see here R can also be calculated from this equation here. Area divided by the wetted perimeter. Now this should agree with this R. This will be a numerical check. Clear? So both the values of R should be the same. This will provide a numerical check from step number 1 to 5. And step number 7 is to calculate the longitudinal slope. Again, Lacey give these equations for calculation of the slope of the channel in the MKS system and in the FPS system. Now these equations for the slope here involves the silt factor. You can see here that the hydraulic radius, it involves the velocity and the silt factor. Similarly, this wetted perimeter equation, and we have the velocity equation here, the discharge and the silt factor. So these equations can be developed, and the development of these equations you can read the textbook on irrigation. But here no need to discuss how these equations are developed. Now in these equations you see that the silt factor that is present. So if the silt factor is not constant, you see that this is the drawback of the Lacey's regime theory. Anyway, this is now a table which gives the values of particle size for various types of alluvial materials. Alluvium, remember anything that is transported by the water, alluvium. So this is a table which is from the textbook by Garg. So you can see here for the silt, very fine, this is the type of material soil. Then this DMM, D sub mm means the average grain size in millimeter, 0.05 to 0.08. If we have fine silt, 0.12, medium 0.16, standard that is 0.32, for which the silt factor is 1. Similarly, we have sand, medium 0.51, coarse sand we have 0.73, and we have other types of materials. So if in a question these materials are given, you can use this table to pick the average grain size and then put in the equation to calculate the silt factor. Now let us discuss an example to design an unlined channel as per Lacey's theory for the data, that is the discharge is 30 cubic meter per second cubics. the mean diameter of silt particle, that is 0.33 millimeter, and the side slopes can be assumed as half ratio 1. So let us solve this. We design this unlined channel using the Lacy theory. So step number 1 is we have to calculate the silt factor. If the silt factor is directly given, we can just use that value. So the silt factor that is F, this is equal to 1.76 into square root of d sub mm. So you can put this value here, and this F, this will be equal to 1.0 something, so 1. Next, step number 2 is we calculate the velocity So the velocity, we have the equation for the velocity. Lacy gave his own equations, you see, to calculate these parameters. So velocity V, that is equal to discharge QF square divided by, take care of the system of units, divided by 140 into whole power 1 by 6. Now you can see the silt factor and discharge, these are known. So plug in the values, we get V equal to 0.773 meter per second. Next, we calculate the area A. Discharge and velocity are known. So step number 3 is to calculate the area A. That is equal to discharge divided by the velocity. Now discharge is given, that is 30. And the velocity we have calculated in step number 2, 0.773. So the area, that is equal to 38.81 square meter. Now the area is calculated. So step number 4 is the weighted perimeter we can calculate. So the weighted perimeter so for that we have the equation P is equal to 4.75 into square root of the discharge. So put the value, this comes out to be 26 0.02 meter. 26.02 meter. Now that the area and the wetted perimeter are known, so step number 5 is to calculate the bottom width and depth of the channel. So we have the equations, that is D is equal to P minus square root of P square minus 6.944 times A, this is the area, divided by 3.472. So area is known, the wetted perimeter is known. Just plug in the value, so we get D is 1.68 meter. Similarly, when D is known, we can calculate the bottom width of the channel, that is equal to P minus 2.236 times D. So this comes out to be 22.26 meter. Next we calculate the hydraulic radius. So we have step number 6. We calculate R. Now R will be equal to 5 by 2 for MKS system of units into V square by F. Now everything is known, so we calculate hydraulic radius is 1.49 meter. Now as a check, we can also calculate R from the equation. This is as a check on the calculations. So this R can also be calculated from area divided by the wetted perimeter. So this is equal to B times a D for trapezoidal channel section plus D square by 2 for the given side slopes divided by B plus a D into square root of 5. So put the values, this comes out to be 1.49, and here it is 1.49 meter. So this is a check. And step number 7 is to calculate the longitudinal slope. So the slope S Again, Lacy give his own equation for the slope S, and S is equal to F power 5 by 3 divided by 3340 into Q power 1 by 6. So just put the values. This S, this is equal to 1n 59 100. So this is the longitudinal slope of the channel. Next, we discuss the drawbacks in the Lacy's regime theory. So the concept of true regime is only theoretical and cannot be achieved practically. The various equations derived by considering the silt factor, as I already explained, silt factor present in the various equations, which is not at all constant. The concentration of silt is not taken into account. The silt grade, the sizes, and the silt charge, the load quantity, are not clearly defined. Again, the equations are empirical and based on available data from a particular type of channel. The characteristics of regime of channel may not be the same for all cases. So these are the drawbacks in the Lacy's regime theory. But no doubt, as compared to the Kennedy's theory, this became the popular theory in the subcontinent. And many channels, many irrigation canals, they were designed based on the Lacy's regime theory. Comparison of Kennedy's and Lacy's theory. So this is a comparison between the two theories. Kennedy theory states that the silt carried by the flowing water is kept in suspension by the vertical components of eddies which are generated from the bed of the channel. Lacy theory states that the silt carried by the flowing water is kept in suspension by the vertical component of eddies which are generated from the entire wetted perimeter of the channel. So here the bed and here the entire wetted perimeter. Kennedy give the relation between V and D, if you remember the critical velocity equation. Lacy give relation between V and R. You can see here velocity V equation, V and R. You see R, V and R. Critical velocity ratio M is introduced to make the equation applicable to different channels with different silt grades in the Kennedy's theory, whereas in the Lacy theory, silt factor is introduced to make the equation applicable to different channels with different silt grades. Cutter's equation is used for finding the mean velocity, whereas Lacy theory gave an equation for calculating the mean velocity. Kennedy theory gives no equation for the bed slope, whereas Lacy theory gives an equation for the bed slope. Kennedy's theory design is based on trial and error. In the Lacy's theory, it does not involve the trial and error procedure.